Okay, so what we're going to do, I said at the end of the lecture last week that we couldn't do the revision of the integration, but I think that would be a terrible mistake. We're going to do the full revision. Actually, it works out now. It's going to be done quite quick. The revision will be done quite quickly, but it's not. What I can do is, so we've got basically, there's kind of there's only 3 extra bits of integration from last semester, and I can incorporate 2 of the extra bits into a general strategy, incorporating what you did last semester and into this. And then the other things, you would have calculated the work done by a force, I think. We'll just see that again. And the third thing is calculating centroids and centres of gravity. Essentially they're formulas, and probably if I can get us anti-differentiating and integrating, that'll be better. So although I'm saying I want to rush on the revision, I'm going to go as fast as possible without rushing. Okay, so page 154. So what we're giving now, most of this section, and actually stuff that we'll probably do for revision or even notes for a lot of the extra stuff we do, has been emailed last week. So it says, it's something like revision of integration or anti-differentiation. It's linked in last week's email. Okay, so we're going to come up with a strategy for anti-differentiating. Anti-differentiating, we do it to calculate integrals. You go into level 7, you solve differential equations. Basically nearly everything in engineering is a differential equation, the maths of it. So for example, Newton's second law is a differential equation. If you want to solve them, you have to be able to anti-differentiate, so that's why we're looking at this. Okay, so the strategy that I'm going to recommend is any integral that you're confronted with, the first thing is you say, can I do it from the tables? If you can't do it from the tables, you try and rewrite the thing you're trying to anti-differentiate. So there's various manipulations which include partial fractions, which if you go into level 7 you will use, they will not appear in this module, and complete the square, which is a special manipulation that we're going to learn in this module. The reason you learn it is all of these things are useful in level 7 in a slightly different context. Number 3, so if the manipulation doesn't work, you're going to try a substitution. Now, you would have called it a U substitution last semester. I'm going to call it a W substitution because we're going to have a different type of substitution here. And it's like with the product rule and the quotient rule, it's okay to use U and V. But this is a kind of a different thing to them. So I'm going to call this one a W substitution. If the W substitution doesn't work, you should try parts. And this strategy actually, if you keep on going into level 7, into level 8, etc., this strategy is a good strategy, and you can add way more things to this, but you don't need to. Okay, so we're going to look at each of the 4. This is going to be new, and we'll look at it in more detail hopefully tonight, and this is going to be new. So both of these are going to be examined, but you probably need to be able to do all the other things as well. Maybe we'll just say that this won't come up in this module. You will need that if you go into level 7. Okay, you would have done it last semester. Okay, so there's a bit of, we'll kind of skip the bullshit as much as possible. The theoretical background as much as possible. Okay, so direct means just doing derivatives backwards. So derivative of x cubed is 3x squared. So this is a way of writing, if you want to say a notation for antiderivative, this symbol and this symbol, anti-differentiate this with respect to x. So now I'm omitting the c's because most of the time we're going to be doing integrals where you don't need the c's. If it is an antiderivative, you have to do plus c. So differentiate x cubed to 3x squared, anti-differentiate 3x squared to x cubed. Derivative of sine x is cos x, antiderivative of cos x is sine x. Derivative of log x is 1 over x, antiderivative of 1 over x is log x. Or strictly speaking, log the absolute value of x, which is in your tables. The derivative of inverse tan is 1 over 1 plus x squared, so the antiderivative of 1 over 1 plus x squared is inverse tan. So that's what I mean by direct. You get a table of antiderivatives like this, so your differentiation tables, you run them backwards. That's an antidifferentiation table, and of course there's also a table of antiderivatives as well. The three functions that people mess up, what I mean by mess up is they assume they need a manipulation or a W substitution or parts, are this one, this one, and this one. These are all in the tables. So a lot of people say doing this module during the day I try and get them to do this, but they just say, oh, it's going to be parts or complete the square, and they forget to look in the tables. The first thing you look at always is the tables, and every one question we do, even the ones in this section, I'll probably say, is it in the tables? Is there a manipulation? W substitution? Okay, we can try parts. All are in the tables. Note finally, linear combinations, you can do them term by term. Now what linear means is if you've got a plus or a minus, you can do them separately, and if you have a constant, you can fix the constant in antidifferentiation. And that's just running this backwards. So if you're differentiating a sum, fix the constant differentiation. Then do this one separately. If they're multiplied together, things are more complicated. Right, so I'll do three quick little examples here. So this is in the tables, this is in the tables, this is in the tables. So do term by term. Now there's no integrals here, so we will do the plus c. So linear means you do them term by term and fixing constants. So the plus means I can do them term by term, and the minus is also, so adding a negative is basically addition. And I'm going to fix the constants. So we'll just say, just to have something to write down equals, I'm going to write, say, call this one I1, this one I2, this one I3. So I1 is equal to, fix the 2. What is the antiderivative of x to the power of 3? X to the 4. So add 1 to the power, divide by the new power. So what is it? X to the 4 divided by 4. Add 1 to the power, divide by the new power. Fix the 3. What is the antiderivative of cos? Sine. Fix the minus 2. Oh crap. Fix the minus 2. What is the antiderivative of e to the x? E to the x. And you should do a plus c on these. Now we could tidy up the first term, but this is revision. I'm going to keep going. So let's look at the next one. So the next one, the 4 over x. The 4 is actually a constant. If you want, you can say it's 4 by 1 over x. They're the same thing. Maybe we'll just write down one thing while we're here. Somebody say this. 2/3. 2/3. 2 over 3 is it's correct, but it's no good for you. 2/3. 2 by 1/3. Whenever you have a over b, it's a by 1 over b. So here 4 over x is 4 by 1 over x. We can fix the 4. And what is the antiderivative of 1 over x?
Natural log of x.
Natural log of x. And being fussy, the log of the absolute value of x, and then plus the c. The third one, so the third one would be the one that would catch people. They would tend to try manipulation or a substitution, but it's actually in the tables. It's here like this. So now in week 11, obviously maths is difficult if you struggle to pattern spot, and I can't really help you at this stage. Just hopefully it goes okay. So it is actually in there because it's like a 1 over a squared plus x squared. How is that an a squared? 1 by 1 is 1 squared. So actually I have 1 over 1 over 1 squared plus x squared. So it's exactly one of these with the a equal to 1. So I'd write I3 is 1 over 1 inverse tan x over 1 plus c. Now you really should be able to tidy that up. I won't do it. What's 1 over 1 equal to?
1 to 1.
And what's x over 1 equal to? X. So that's just inverse tan of x plus c. So that's what I mean by direct. Just doing straight from the tables. Okay. The next one, manipulation. Now there's lots of different things that fall under manipulation. But for all of these, we're going to, when we do our examples, we're going to see can we do them using the tables first. So there's a whole host of functions that need a bit of manipulation, so you change them, you rewrite them before they can be anti-differentiated. It'd be impossible to list all the possible manipulations, but here there's a selection of common ones. So if you have 1 over x to the n, now here's a little thing, just a little explainer. If you multiply numbers together, you get positive powers. If you divide, you get negative powers. That's what negative powers are, dividing. So 1 divided by x again, divided by x again would be divided by x, divided by x, divided by x, divided by x 3 times x to the minus 3. And then, so say if you've got 1 over x to the n, you would rewrite it as x to the power of minus n. So that's what I mean by a rewrite. Now I haven't anti-differentiated. These are equal. These are the same thing. Is this in the tables? Or something that's like this in the tables? Yeah. So what we have in the table is the antiderivative of x. Now I'm not going to use n because it might confuse. I'm just going to use, say, a. X to the power of a dx is x to the power of a plus 1. So you add 1 to the power and divide by the new power. So for example, if you wanted to anti-differentiate 1 over x to the 4, that is not in the tables. So it's not, you can't do it directly, you do a manipulation, and the appropriate manipulation is you write this divided by x 4 times is x to the minus 4. And what will the antiderivative of x to the minus 4 be? Yeah, so minus 4 plus 1 is minus 3. So x to the minus 3 divided by minus 3. And we'll do plus a constant. Where does this formula have a problem?
Minus 1.
If you throw in a minus 1. If a is minus 1, you get minus 1 plus 1, you get division by 0, that's wrong. So a is not equal to minus 1. Just taking it up here, if you have x to the minus 1, that formula doesn't make sense. Does anyone know the antiderivative of x to the minus 1?
Natural log of 1?
Natural log. Because x to the minus 1 means divided by x once. And that is in the tables, that is log of the absolute value of x. So that's just a small thing to show us. So that's one manipulation, negative powers. Another one is surds. So say if you've got something like this here, now this is, I'm just going to write, now this is in the tables. So the way this works is a root is, so like a square root is 1 over 2, a cube root is 1 over 3, this is an mth root, this is 1 over m. So this you can, there's different ways I can write it, but I will tell you what I'm about to do is in the tables. So x to the power of m, and an mth root is all to the power of 1 over m. And then if you know your way around indices, repeated powers, you multiply the powers. Now you would go straight from here to here if you needed to do this manipulation. So we'll give an example. If you want to anti-differentiate the cube root of x squared, that is not in the tables. So you have to do manipulation, and you need to know your stuff within the space. So you go into your tables and basically use this. So it'll be x to the power of 2 over 3. Have I antidifferentiated it?
No.
No, I've just rewritten it. And now, what is the antiderivative of x to the power of 2 over? Is this in the tables?
Yeah.
Yes.
Plus 1.
So plus 1. So 2/3 plus 1. You can go to your calculator if you want. You'll get 5 over 3. And then divided by 5 over 3. I'm not going to worry about the manipulations. I'm just going to leave that like that. Plus c. Then the other thing that you might want to do is multiply out. So this is going to come up, this is going to be important later on. Around 9:30 on the last class probably. So now the one that you'd probably be more like down the bottom, and actually this would be harder than what you need. Most of the ones that we'll be looking at actually won't be that hard. But say if you're looking at this one, so this, now you could rewrite these separately, but they're multiplied together. That's no good. So if you got things multiplied together, you need to multiply them out. So you do root x by 1, giving you root x. What's root x by root x?
X.
X. Now this is fine. This is in the tables because it's x to the 1. What are you going to do with the root x?
X bar of that.
X bar of a half. If you write no number here, this is the second root, and then you can actually antidifferentiate it then using the tables. So if it's things multiplied together, you can't send them back. You can't send these back separately if they're multiplied together. Only if they're added. These you can send back separately. So you have to multiply out. Here's another one you have to multiply out. Here you carefully do x squared plus 1 over x squared by x squared plus 1 over x squared. You get this. Is this in the tables?
Yeah.
What do you have to differentiate to end up with 2? 2x. The antiderivative constant is constant times x. If you differentiate 2x, you get 2. The 1 over x to the 4, is this in the tables? One over x to the 4 in the tables? No. Only 1 over x is ln of x. If it's anything else, it's not. Is 1 over x to the 4 in the tables? No. So that means the next thing that is a manipulation. Can you rewrite 1 over x to the 4?
X minus 4.
X minus 4. Tables. Not quite tables, but it's close as tables. So you can do it 1 by 1. Okay, so the manipulations.
Where do you get the 2 from?
You do it just from the start of it, sorry, just so we can...
So squared means multiplied by itself. So x squared by x squared is what?
X bar of 4.
X to the power of 4. X squared by 1 over x squared. I'm just going to write this just as it's written. X squared by 1 over x squared. 1 over x squared times x squared. And I'm going to do 1 over x squared times 1 over x squared. What's x squared by 1 over x squared? 1. Because it's just x squared divided by x squared. What's this then? 1. Same. So that's your 1 plus 1 giving your 2. How do you multiply fractions together? What do you mean by cross?
Can you cross multiply
What do you mean by cross?
by 1, or what is it? 1 by x squared?
No.
By
Multiply the
No.
bottom and you multiply the top, is it?
Top, bottom, bottom for multiplying fractions. So this is 1 by 1 is 1. X squared by x squared, which is 2x's, 2x's, 4x's. So that's what happened there. Okay. So we got dividing in. One thing to need this one is importantly. So for example, if you have, here's some examples, right? So here's one. This is not in the tables. So yeah, I'm going to kind of gloss over this one. I don't think it's as important. This one is more theoretical understanding. You won't need this one. Trig manipulations you will not need. Okay, this is a good resource, by the way, for next if you're going to level 7, but you don't need it. Other, slightly more advanced but routine partial fractions, which you did in last semester and you'll need next semester, and completing the square. You will need this completing the square next, so if you're going to level 7, and we'll look at it a bit later on. We'll see that in this module. An example of the use of partial fractions for antidifferentiation. This isn't in the tables. A manipulation is a special manipulation which is partial fractions. You can write this like that, and then you can do a little W substitution, W substitution, W substitution. Not we're worrying about. This is the one we're going to be looking at. A special manipulation for 2 particular families of antiderivatives. Writing, so what we'll be doing, and as I said, we might see some of it tonight, rewriting this like this, and then when we're that rewritten, we'll be kind of thinking about the